Hello everyone. In this recording, we're going to discuss encoding and data interactivity for graph-structured data. So encoding interactivity, the idea is you want to change the visual encodings you have for each of the graphical marks depending on some sort of user inputs. So concretely, one thing you can do is you can just highlight. So in this example, I'm highlighting all the neighbors of whatever node I'm closest to, right? So it's giving you a sense of which nodes are more connected than others, right? So this is the high school example. The corresponding thing for an adjacency matrix view would be like this. So here, whenever I hover over an edge, so each square is an edge, it's showing me both what are the nodes that it's connecting, those are the larger labels, but also what are the direct neighbors of whichever node is currently being selected, right? So if I go to the left, the one that's large is the currently selected node, or the one of the edges, or one of the nodes corresponding to that edge, and all the smaller labels are all the neighbors of that node. And so you get an idea. You have an edge, they're the two nodes, and then they're all the neighbors of each of those two nodes, and I'm able to see that very easily using this highlighted approach. Remember, we had talked about how topological queries are difficult in adjacency matrix views. This is at least making that neighborhood topology query a little bit easier. Okay, so how do you build an example like this? In both of these, what I did first is I constructed a new data structure that contains all the neighbors. And so here, these are all the neighbors of node 0. Here's the neighbor for node 1. So that makes it so that I don't have to recalculate the neighborhood every time the user interacts. If you had to do that recalculation, it would slow things down. All I have to do now is I just have to look up what is my current neighbor, or what is my current node, and I can immediately fetch all the neighbors. Okay, so once that data structure, all we need to do is we need to change the visual encodings depending on the interactivity. So the example for the first one, the node link, what I was doing is I was changing the adders for the circle. So it's just changing the fill. It was either black or red. And what it's doing is it's just checking node by node, are you within the currently selected set of neighbors? Right, so I looked up in that data structure, I figured out what is the currently selected set of neighbors, I checked whether you were contained in it. If you were not contained in it, you were black. If you were contained in it, you were red. And I just rerun this kind of adder update every time the mouse moves. Okay, similar thing going on for the adjacency, right? So it's changing the rectangles, it's changing the labels, but it's similar for both. So here is just for the X label. What I'm doing is, if you are kind of the immediate neighbor, or if you are kind of the one of the nodes on either side of the edge, then I'm going to make you larger than the rest of the labels. And then if you are within the neighbors, I'm going to make sure that you are visible. But if you are not one of the neighbors, I'm going to actually turn the text invisible. So actually, if you go back to that example, the labels are actually all there. You can't see it, but they're there. It's just I've made them kind of totally transparent. And you just rerun that every time the user's mouse goes over a new rectangle. Okay, so another point I want to make is there's really nothing that special about interactivity in the graph setting as far as implementation is concerned. Everything that we've learned about implementation for interactivity in D3 can be applied to the graph setting. So an example, remember we had used these Delany diagrams so that we could make very smooth interaction with scatter plots. You can do the same thing in networks. Right? So here, a little little video, if it would load. Let's see. Okay, so what it's showing is you don't even have to click on the individual node. As long as you click on that overall kind of cell containing the node, it will move the node. And so that can make it much easier to interact with the graph than having to kind of zoom in and figure out exactly clicking on the one link. Okay, and just like the Voronoi idea, other kinds of common interactivity that we'd had before, we've done a lot of coordinated views with brushes. You can also do coordinated views with brushes in the network context, right? And that turns out to be quite useful for data interactivity. So far we've been mainly focusing on encoding interactivity, let's think about data interactivity. So we might want to change the nodes and edges we show depending on the user's interest. Right? So a simple example would be like if there are certain groups of edges or types of edges that you want to display depending on what the user selects, right? And then you can change the edges that you show, or you might change their encodings too. So here's an example though of not a group, but you might have in here is the degree, right? So I know the degree of every single node, and it has this kind of distribution. And when I select like this, right? Or sorry, this is not the degree, this is the centrality, right? So when I select just the very central nodes, these are nodes that kind of lie along the main highways of the network. So I've trimmed away everything else. These are, if you were any other node and you wanted to reach kind of a path between any pair, you would typically fall along these kind of highways on the network. These are the highly central nodes in the terminology, right? And then, these are kind of like the more peripheral, like things that, not really central highways. They're just connections that you could usually avoid if you needed to do any major path, right? So the point though is like, I'm just using the same kind of brushing interactivity we've used in a lot of situations before, but now to do some sort of data interactivity in a network. I'm just filtering which edges I show based on some statistic that we've calculated about them in advance. Okay, how is this done? This is just the usual enter-exit update pattern together with the brush, right? So we pre-computed the edge centrality, so we know which edges we're going to remove or add depending on which part of the histogram we're in. And then as the user brushes, you just check. Does this currently drawn edge have a centrality value that's within the brush? If it does, then we keep it in the display. If it doesn't, then we remove it. And we continue running the simulation, but with the forces updated to reflect the new edge pattern. Okay, so this is an example of filtering. We're just removing a lot of marks. Another kind of data interactivity is you might try to aggregate. That's another way of simplifying things. Instead of removing things entirely, you just clump them together into similar groups. So this is sometimes called semantic zooming. So in contrast to the pan zoom that we saw in the view interactivity, semantic zooming is like you are able to focus your attention on some part that the user shows interest in, but you're not just simply resizing things, right? You're kind of reprioritizing emphasis without having to just physically change size. So an example of this kind of changing emphasis, there's this nice example where these are actually already aggregated nodes. Each of these kind of nodes actually belongs to a little cluster, right? So now I'm drawing the entire cluster. Anytime I click on them, I show the entire cluster. So it's a kind of semantic zoom, right? It's not physically zooming things, but I'm able to see a little bit more information when I interact. And then I can collapse them back, so I can re-aggregate. So you can imagine this being useful in any situation where you can give a high-level overview. So here's kind of giving an overview of the skeleton of the network. And the user can query like, well, I'm actually interested in this particular subset of the network. And if I'm interested in that particular subset, I click on it and I see all the nodes that belong to it. Okay, so filtering and aggregation. They're kind of either top-down or bottom-up views that can, they're kind of bottom-up or top-down ways of navigating the graph, right? But they both kind of depend on being able to see the entire graph at once. You either see the entire graph as some big overview, and then you kind of expand it out, or you see the entire graph with all the details and you try to collapse it all in, or prune everything away, right? An alternative is you do something intermediate. So this idea is you start at some neighborhood, maybe the user can search for a neighborhood of interest, and then instead of showing the entire graph, you just show that part that's interesting to the user right now with some sort of pointers to if they want to learn a little bit more about some property of graph or some kind of type of node, they should move in one direction, right? So that's described in this paper here. It's doing something that they call a degree of interest calculation. The way it works is you start off in some neighborhood. It's not showing the entire graph, but you get the sense that the graph continues on beyond the border of the current view. And there's a calculation of what is the degree of interest for all these different areas, right? So it's kind of saying the colors will tell you which nodes do you want to go, which nodes do you want to zoom further and pan towards so that you get a little bit more information, right? So yeah, it basically is giving some indication of what are the more interesting areas to pan and zoom towards. Okay, so a little bit different from overview plus detail, but kind of an interesting idea for whenever you're in a graph situation. So we've reviewed view, encoding, data interactivity in the last two recordings. So you should see that in addition to just there being a lot of visual encodings, there are actually a lot of different strategies for interactivity in graph data as well. So depending on your problem context, you can draw from quite a variety of potential techniques.